Hello everyone. We'll start up with chapter 12, lesson 3. We've finished lesson 2 of light waves. This is the new lesson of light waves and color. Have you ever thought why flowers look different in color? For example, why this one looks red, or why does the sky looks blue? The study of color and the way to answer questions such as this, why they look in this way, begins with the study of light. Now, visible light from the sun comes to earth as white light traveling through a space in the form of waves. Visible light contains a mixture of wavelength that the human eye can detect. When these wavelengths are separated, we see them as different colors. This happens when light waves are refracted as sunlight passes through raindrops. Different wavelengths are refracted in different amounts. Long red wavelengths are bent the lost, you see here. Then you have and their short violet wavelengths are bent the most. Recombining all the wavelengths of visible light produces the white light. Now, how this refraction can happen, we can do in two ways. First, we can do it through a prism, which is a triangular piece of glass or plastic which can bend the light. This refraction separates visible light into red, orange, yellow, green, blue and violet wavelengths that make up white light. Now, another way to bend light waves is to use a diffraction grating, such as this compact disc or CD. You can see different color wavelengths here in a parallel slits kind shaped. Now, diffraction, like gratings and prisms, enables scientists to study the properties of light, and this is how Sir Isaac Newton observed the sunlight passing through a prism and emerged as bands of different colors. Newton hypothesized that sunlight was naturally made of different colors of light. He called the colors a spectrum, which means it's a Latin word meaning appearance. We now know that the wavelength is refracted at a different angle, and that this is what produces the different bands of colors. Now let's see an example. Let us say sunlight striking an object may be reflected. Now, reflected or absorbed. The light that is reflected determines the color of an object. Let us say here, for example, the sunlight striking a leaf. Many wavelengths are absorbed and used in photosynthesis. Remember the process of plants making the food. Only green light is reflected, so the leaf appears green. And so this is refraction. Why you see things in different color? An object that reflects all visible light will be looking white, and an object that absorbs all the visible light appears black. Now, there was another scientist called William Herschel who explained another answer for a question. For example, we might be thinking that, is there other than visible light? So he explained it by his experiment in 1800s. He placed thermometers in different bands of light from a prism. He also placed a thermometer just outside the red band of light, where there was no visible light at all. So the red light had the highest temperature of the colored band. However, to Herschel's surprise, the area just beyond the red band had an even higher temperature beyond the red. Now, this is where he correctly concluded that there was another form of energy in sunlight that the human eye cannot see or cannot detect. Today we know that energy from the sun travels in many type of waves. Visible light make up only a small portion of this wave. So we have electromagnetic spectrum that contains the full range of wavelengths. The spectrum is arranged from longer wavelengths with the lowest amount of energy to shorter wavelengths with the highest amount of energy. It consists of radio waves, microwaves, infrared waves, visible light, UV, X-rays, and gamma rays. Radio waves have the longest wavelength and include transmissions of you have AM radio, short wave radio, television, FM radio. Next to it in the electromagnetic spectrum is the microwave. Microwaves are used in you have radar, satellite systems, as well as ovens that cook food quickly. Infrared rays. The infrared waves next in the spectrum are typically felt as heat. Infrared waves are given off by the sun and other sources of heat, such as electric stove burners and active volcanoes. The wave that Herschel, also remember the scientist, discovered were infrared waves. Then we have the visible light near the middle of the spectrum. We see these wavelengths as colors that range from red to violet. After visible light in the spectrum, we have the UV light or ultraviolet rays that carry more energy than visible light waves do. And you know that UV rays and other high energy waves can damage people's skin and eyes. The ozone layer in the atmosphere, the upper atmosphere, provides some protection against this harmful electromagnetic wave. After UV rays in the spectrum are X-rays and gamma rays. These can pass through many substances, including soft human tissue. Because of this property, the X-rays are used to make image of the hard parts of the body, such as teeth and bones. X-rays are also used in airports to screen luggage and other cargo. Gamma rays have very short wavelength. The wavelength is very short, and they have so much energy they can even pass through some metals and concrete. So gamma rays have many applications in science. Right, now how do colors mix? Different color models actually are used in understanding the relationship between colors. Each color model is named after its primary color. Primary colors are not produced through the mixing process. They are natural. Secondary colors are produced by blending primary colors. Now, the traditional color model, such as RYB, red, yellow, blue color model, while it is useful in art, but the model does not include all colors, such as some shades of green or cyan or magenta. The RYB model is still reflected maybe in art classes, but scientists now use more accurate color models, such as the RGB, the one that you can see here. The red, green, blue primary colors of light combine and produce almost all colors. The RGB color model is an example of additive color mixing. In this color model, these three primary colors can combine and refract all colors and produce white color, as you can see here. Then we have the CMY, the cyan magenta yellow color. This model uses subtractive color mixing. This color depends on the ability of substance pigments. Now, pigments are tiny solid particles that provide color to absorb wavelengths of light. The ink cartridges in the color printers, they combine certain amount of primary colors to produce other colors. So when all the three pigments combine, this produces the black color. this is the end of the lesson. Thank you very much for listening and understanding. If there's any question, please ask me, and don't forget to do the section review or lesson review in your workbook. Thank you very much and stay safe.